Okay, welcome back. Next we are going to deal with pHs of weak acid solutions and weak base solutions, which is predominantly what we deal with. We have a lot more weak acids and weak bases than we have strong acids and strong bases. So let's look at calculating the pH of a weak acid solution. This is going to seem really familiar. We're going to use our ice chart, and we'll be doing small k problems. And typically after you do your ice chart, your small k problem, then it'll actually ask you to calculate the pH of the weak acid, so you'll do a pH problem right at the end. For example, the one we're going to try right here is calculate the pH of 1 molar hydrofluoric acid that has a Ka of 7.2 times 10 to the negative fourth. And once again, most of our problems are at 25 degrees Celsius. This one will be at 25 degrees Celsius as well. So just like what we did before, we have to consider all of the species that exist. So we have our weak acid, which is hydrofluoric. Whoops. And because it's weak, we have to have an arrow going both directions. And that gives us hydrogen ions and fluoride ions. And you'll notice in this particular problem that it also gave you the Ka value, which you could also look up. It's in that chart on page 658, which is 7.2 times 10 to the negative fourth. And check your PowerPoint, because I think I have negative 14th on your PowerPoint. Double check that. It should be to the negative fourth. This is definitely a weak acid because it's not one of our 7 strong. And remember, we not only have this happening here, but as always, we have the water as well. And it's undergoing its autoionization process. And in this particular case, if you want to, you can actually compare the Kas and the Kw together. 1 times 10 to the negative 14th at 25 degrees Celsius. And looking at these two components by comparing the Ka to the Kw, you can figure out which one is the stronger of the weak acids. And in this particular case, it's our hydrofluoric. That's a much larger value than our Kw. Now, before we compared our molarities, and we could actually compare our molarities here as well if we wanted to. This is 1 molar, and remember, 1-to-1 ratio exists, so they are all 1 molar. And we know by default this is 1 times 10 to the negative 7th molar and 1 times 10 to the negative 7th molar. So you could do it either way here. You could compare the Ks, the Ka to the Kw. Our Ka is much bigger. Or you can also look at the molarities that are present. The molarity of the hydrogen ions from our weak acid is a lot greater than the molarity of our hydrogen ions from our water. So we're going to ignore water. And we're going to start this problem as ice. And the reason that it has to be ice is because we got that arrow going both directions. Weak equals ice every single time. Weak equals ice. So we will start with our weak acid again. And set up our ice. And we know to start off with, we have 1 molar of our HF. But now, remember, when we initially start off, we don't have any of these other components over here. There's none of that, and there's none of that. As always, if we don't have any products, that automatically means our shift has to be to the right. So here we're going to have You know what? I lied up here. You can't do that. If we could do that, then we wouldn't have to do anything else. We don't know those concentrations because it's an arrow going both directions. That only works, it only works the other way when it's a strong acid. So scratch that, forget I ever said that. When it's weak acids, you have to compare Kas to Kws. One more time. When it's a weak acid, you have to compare a Ka to a Kw. Okay, so we know we have to shift to the right, so HF is going to change by minus X. We got to make some of this other part. So we have 1 minus X, X, and X. Whoops, not a plus sign. X. Now, we want to write our equilibrium expression. Ka equals the hydrogen times the fluoride over the hydrogen fluoride. And once again, remember, we are going to do our ice problem, and then we're going to do a small k problem because 7.2 times 10 to the negative fourth is a small k. And remember, what that means when we have small k's is we can ignore the change in the reactant. Ignore change in reactant. So now plugging in, 7.2 times 10 to the negative fourth equals, on top they'll both be x's, and on the bottom we'll have 1 because we're ignoring the change. So making this simplified, we have 7.2 times 10 to the negative fourth equals x squared. And all we need to do to come up with our answer is take the square root of both sides. When we take the square root of that, we end up with 2.7 times 10 to the negative fourth. And this is a molarity. Here in this problem, we solve for x. X is a molarity. Now, the other thing I want you to be really careful of, it's the molarity of what? Well, in this case, it's the molarity of both our hydrogen ions and our fluoride ions, but once again, we don't really care about the fluoride because we're solving for the pH of this. So X is also the concentration of our hydrogen ions. That's the part that's really important because we want to get to pH, and in order to get to pH, you have to have H first. So I'm running out a little space here, so let me go to the next slide so that I can solve for the pH for you. So pH equals the negative log of our hydrogen ion concentration, and our so the pH equals the negative log of 2.7 times 10 to the negative second. Now, this is not one where you can use our little cheater rule, and the reason we can is because our coefficient is not 1. So yes, you will have to pick up your calculator this time, and our pH is 1.57, which is a pH for an acid. If you came up with a pH greater than 7 when you do this problem, your brain should automatically think there is a problem because acids have to have a pH below 7, bases are pH above 7. So you can do a little quick check to see if this falls in the acidic range on the pH scale. Okay, let's see what else we can practice on. Let's try one that is actually a mixture of acids. And so we'll look at this mixture of acids and kind of figure out which one do we need to use. And this should be example 14.9 in your textbook. But once again, remember with these particular problems, I told you to kind of ignore what Zoomdoll does. He makes them a lot more difficult than they need to be. So if you just wanted to kind of read through the problem, it is 14.9 on page 670, but I'll work it out for you in a little bit more simplified manner. So what do we do when there's several acids? In this particular case, we have hydrocyanic acid, our nitrous acid, and then also remember there is always water there as well. And if you look at the problem, it also asks you to calculate the concentration of the cyanide ion in this solution at equilibrium. And so I'll show you how to do that. So first off, we have hydrocyanic acid. Hydrocyanic is weak, so our arrow will go both directions. If you're looking at your textbook, they did give us the Ka value for this one. It's 6.2 times 10 to the negative 10th. So this is a really weak acid. It would give an excellent conjugate base. Cyanide is a really good conjugate base. And this was 1 molar. We also have nitrous acid. Weak acid. It'll go into hydrogen and nitrite. And it has a Ka of 4.0 times 10 to the negative 4th. And this is 5 molar. And of course, we always have water. I'm not actually going to write the autoionization of water. This time I know it's there. So I'm going to write down my Kw just so I remember, yeah, water is present. But I don't need to write that equation every single time. I just need to remember that it's there. So as we look at these, we need to figure out, of these three things, who's the source of the hydrogen ions. And so we can knock out water because it's 1 times 10 to the negative 14th. That's a really small value. We're also going to knock out our hydrocyanic acid because look at its Ka value. It's not much bigger than our water. So where we're getting our hydrogen ions, in this particular case, they're coming from our nitrous acid with a Ka of 4.0 times 10 to the negative 14th. And so what we need to solve for again is we're going to come up with our pH, and that's going to be based off the hydrogen ions from the strongest of our weak acids. And we also need to figure out what's the concentration of cyanide that's present in this one. So let's go ahead and start out with our ice chart first in our equation. And we know we have 5 molar nitrous acid, but once again, we don't have any of the products to start with. So that automatically means we have to shift to the right. We are going to reduce the amount of our reactant, and we're going to add to our products. So this becomes 5 minus X, X, and X. Now, once again, this is going to be a small K problem because, you know, even though it's the biggest of the Kas that we have here, it still qualifies as a small K problem. So we've got our ice chart. I'm actually going to flip over to a new slide so I have a little bit more space to work. Let's start off by writing our equilibrium expression. Ka equals the hydrogen, our nitrite all over our HNO2. Our Ka value for this was 4.0 times 10 to the negative fourth. We had X for both our products. And this time we did have a different concentration for our nitrous acid. It was 5. Now remember, let's go back just 1 second. Remember, because this is a small k problem, we're going to be able to get rid of that. Small k equals ignore the change in the reactants. So we'll go ahead and remember to ignore that. So that's why on the bottom on the next slide, that's why I just have a 5 down here, because I'm ignoring that change. So this takes us out to, first thing I'm going to do is I'm going to multiply both sides by our 5, which gives us 2.0 times 10 to the negative third, and I'm going to simplify x times x and make that x squared. So just so we remember, I multiplied both sides by 5. Put my x's together to give me the 2.0 times 10 to the negative third equals x squared. Next, I'm going to take the square roots of both sides, and that gives me 0.045 molar equals x. Remember, when it's an x, it's a molar. Now, the other kind of critical thing you should do here is make sure that you remember that this is the hydrogen ions. And I only stress this in this particular chapter because sometimes when you come down to X, as we see in the weak bases, this is going to be your amount of hydroxide. So you really do want to make sure you know what that X represents at the end of the problem. Since we have our hydrogen here, that means we can immediately go on to calculate our pH. If this was hydroxide, we got a little more work to do until we can get to our pH. So we'll take the pH equals the negative log of our 0.045. And once again, it's not a coefficient of 1, so we will have to use our calculator. And we come up with 1.35 for our pH. And once again, definitely falls in our acidic range, so we can be fairly certain we've done that correct. Now, something else we need to do with this particular problem is it asks us to find out the cyanide. And this is kind of a nifty little thing that happens here. We are first going to write our, whoops, I'm going to need to add in an extra slide here real quick. And I'm going here. Okay, so we're going to add in an extra slide, and we're going to go back, and we had our hydrogen cyanide, and it dissociates into hydrogen ions and cyanide. And we had our Ka, which was 6.2 times 10 to the negative 10th. We can go ahead and write an equilibrium expression for this. Oh, we did have one other piece of information. We knew that this was 1 molar. And so our Ka equals our hydrogen, our cyanide, over our hydrogen cyanide. Now, one of the little tricks to this problem is you got to remember, where did our hydrogen come from? So that we were able to calculate our pH. This hydrogen is not from our hydrogen cyanide. This hydrogen came from our nitrous acid. So when we go in to fill in a value for the hydrogen, we need to fill in the value for hydrogen that came from the previous problem that we worked. So we have our Ka, We know the concentration of our hydrocyanic acid. We know the concentration of our hydrogen from our previous problem that we worked out. So we can solve for our cyanide. So we have 6.2 times 10 to the negative 10th. From our previous problem, we know that this is 0.045. We are looking for our cyanide, and we know that our hydrocyanic acid was 1 molar. So we end up simplifying 6.2 times 10 to the negative 10th equals 0.045x. Divide by 0.045 and we get 1.4 times 10 to the negative 8th molar equals x, which x in this case is our cyanide. So once you've got that hydrogen ion concentration from the strongest of your weak acids, that is the hydrogen ion concentration you want to use for any other problem that you work throughout. Okay, one last thing I want to show you deals with what's known as percent dissociation. And with percent dissociation, it's become a little less important over the years. In fact, as I'm looking at this, I think I may have entirely skipped it last year. Yeah, let's go ahead and skip it. We have to cut some things here as we go along, so I think that's something we're just gonna cut and keep moving. Okay, so let's move on into the bases. And what you're going to find is this is pretty much going to work exactly like what we did for the acids, with one exception. We're going to have to do a little bit of work on our initial equation that we write. So with our bases, they produce hydroxide in aqueous solutions, or they can accept a proton. And remember, we typically look at them as accepting a proton. And what we're going to find out is that when they accept that proton, they actually end up making hydroxide in the process as well, because they are accepting protons from from water. Just like before, this is stuff you already know. Strong bases completely dissociate. So when we are working with the strong bases, arrow going one direction. Now, this is where we get all of our weak bases, because all of our weak bases come from substances that don't have hydroxide. What they typically do is have at least one unshared pair of electrons, and that unshared pair of electrons joins up with the hydrogen ion. That's how it can accept that hydrogen ion and form a covalent bond. And when that happens, we end up producing hydroxide at the same time. So let me show you an example. If we put ammonia in water, and we can see how that happens. So I'm not going to show you with the electrons and everything. So we take ammonia, NH3, and put it in water. And we know that ammonia is our base. Well, if ammonia is our base, then water has to be our acid. That means the base ammonia is going to accept a proton from water, and water is going to donate that proton. Well, when ammonia gains a hydrogen, it becomes ammonium. And that leaves us with our water molecule. All that's left is our hydroxide. So ammonia even though ammonia doesn't have any hydroxide on it, it does increase the amount of hydroxide in our solution when it is dissociated or reacts with water. You'll notice that with our acids, we never added water in with an acid. We don't need to do that. With the bases, you have to. Every equation we write will be a base plus water. Now, just like before, when we have base and we have acid, we also have our conjugate acids and we have our conjugate base. And so remember, our conjugate acid is our base molecule plus a hydrogen. So here is our conjugate acid. And our conjugate base is our acid molecule minus a hydrogen. So here's our conjugate base, and once again we have two conjugate acid base pairs in our problem. So let's go ahead and look at one more slide here, and then we'll do some problems. The reaction of a base with water. Now, so here, same thing I just had up there for you. Let's pop a few. Oh, you know what? I should have changed a few things in here, and I'll fix that for you. I forgot to do that. So we have our reaction. Notice right here, this is the really important part right here. Make sure you highlight this, do something. You always are going to have to do that step. If you don't do this step, then you don't end up with any hydroxide, and you really can't do anything with the problem. So every base problem that we work has to start out with the reaction of a base with water. Now, if we were going to rewrite this Kb expression here to make it accurate for what we did, we'd put our conjugate acid up there, and down here below we'd have our NH3. Notice this is a Kb instead of a Ka. It's for the base dissociation constant instead of the acid dissociation constant. These problems essentially work exactly what we did before. Weak bases have very small Kb values. The calculations are saying we do the ice problem for whenever it's weak. Just like we did before, we want to consider water, see if water's there, and what its concentration of the hydroxide would be, or actually comparing the Kb to the Kw. Once we figure out our greatest contributor of hydroxide, then we can go and do our ice problem. Once we do ice, then we go to our small k problem. And now here's where the switch is going to come. When we finish the small k problem, we're going to have the concentration of hydroxide. We are not going to have the concentration of hydrogen. And there are a couple ways you can go about fixing the problem at the end. And as we work through, I'll show you how to fix it. It's very easy. So let's do a little bit of practice with a weak base. And you're going to see this is just exactly like what we were doing before. The problem I'm going to work for you, if you want to follow and look at the problem in the book, it is page 678. Example 14.13. What we're going to do is calculate the pH for a 15 molar solution of NH3 with a Kb value of 1.8 times 10 to the negative fifth. And that's all they want us to do. We don't have to do any extra calculations. So start off the same way. Now, here's the difference. It's a base. Bases have to be reacted with water. And so we'll get ammonium and our hydroxide. We know that we're starting with 15 molar of that, and our Kb is 1.8 times 10 to the negative fifth. Now remember as well, we always have water as a part of this problem. So you can write out the auto ionization, or if you just want to remind yourself, put 1.0 times 10 to the negative 14th. We're going to compare the Kb to the Kw. Automatically we see our Kw is a lot smaller than our Kb. I'm going to say 99.9 times out of 100. That's always going to be the case. You're going to eliminate the water. The only time you really have to be mindful of this is when you got really teeny tiny concentrations of either your acids or your bases. Okay, so weak. Remember we talked about this before. Weak equals ice. So we got to start with our ice chart first. So we'll write that equation one more time. We know that we have 15 molar of our ammonia. We do not care about the water at all because water is a liquid. So all the way down, we're just going to completely ignore that part. None of that, none of our products. Now we know that this is automatically going to shift to the right because we don't have any product. Minus x plus x plus x. 15 minus x, x, and x. Just like before, this is another small k problem. So we can cross that out. Say small k equals ignore the change in the reactant. Can ignore that. And so then this is pretty much exactly what we've done before. I'm going to go ahead and move over to another slide so I have a little bit more space to work. Whoops, I'm going to need to add a slide in. Okay, so we are down to writing our Kb expression. Okay, and so we are able to start plugging in. Our Kb is 1.8 times 10 to the negative fifth. Ammonia is x, hydroxide is x, and our ammonia was 15. So we'll go ahead and solve. The first thing we're going to do is multiply both sides by 15. That's going to give us 2.7 times 10 to negative fourth. I'm going to go ahead and put my x's together for x squared. And then I'm going to take the square root of both sides. This is exactly what we did before. This is equal to 1.6 times 10 to the negative second molar. We remember x molar. Now, here's where you have to be careful. This answer is not hydrogen. This answer is for hydroxide. So when you solve, if you took the negative log of this particular value, you would not be getting the pH. You would be getting the POH, which is fine because we can very easily switch a POH into a pH. So that's actually what I'm going to do. I'm going to go ahead and solve first for the POH. And the negative log of 1.6 times 10 to the negative second is 1.80. That's the pOH. Now, to come up with the pH, remember I told you about that handy-dandy little equation? We're just going to take 14 minus 1.80, and that gives us 12.120 for the pH of that solution, which makes sense. It's a weak base. It had better be above 7 for its pH. So you can see this really only has one tiny difference to it. It's just that part at the end right here. This is where you have to be careful. When you start with a weak base, your X is going to be for hydroxide. Your X is not going to be for hydrogen. So you have a little extra step to do that down there at the bottom in order to solve for the pH. And so you can see it's exactly what we were doing for the other one, so it's really pretty easy. I do want to talk about one more thing, a little bit of discussion about polyprotic acids. There might be some simple questions on the AP exam. They don't ask the monster question anymore that used to take a whole page in order to answer, but I just want to make you a little bit aware, a little bit more about polyprotics. Put a few things up here. Remember, we talked about it before when we did that previous example in the first lecture with the sulfuric acid. Polyprotic acids are any acids that can furnish more than one proton. Here's a couple examples. Sulfuric and phosphoric are the ones that we most commonly run into. And they dissociate in what's known as a stepwise fashion, which means they lose one hydrogen at a time. You don't lose two hydrogens, you go one hydrogen at a time. Well, what's kind of interesting is that their Kas follow a pattern as well. The Ka of the first hydrogen you lose is going to be bigger than the Ka of the second hydrogen you lose, which is then bigger than the Ka from the third hydrogen you lose. So with polyprotic acids, as you lose more and more hydrogens, your Ka value gets smaller and smaller and smaller. Why does the loss of the second and third protons occur less readily? As we decrease take a hydrogen away, what we do is we increase the attraction of the phosphate or the sulfate for those remaining hydrogens, so it gets harder and harder to remove. For most acids that we are looking at that are polyprotic, first association is really the only one that matters. That's where our hydrogen ions come from. There used to be a tricky rule with sulfuric acid based on its concentration. They don't do that anymore on the AP exam, so I mean, don't even put that out of your mind. Don't even worry about that at all. That is unnecessary. You may notice that there are a few more things in your PowerPoint with the acid-base properties of salts. We're going to kind of leave that be and skip that for the sake of time. Doesn't seem to be on anything on AP Insight. I haven't found it there yet. And it's also not in your Princeton review, so I feel pretty confident that will be okay. Look to the wiki page for some more problems that I will be posting, and I will see you on Tuesday.